thank you for introduction. The title of the talk is Quantum Error Mitigation and its application. The outline of the talk is as follows. First, I'll talk about the background of this research. And this research is mainly about quantum error mitigation. So, I'd like to talk about the concept of error mitigation. And after that, I'll talk about the interesting applications of the quantum error mitigation. The first one is the application to fault-tolerant quantum computing. And the second one is the application to quantum metrology, which is also called quantum sensing. Okay, this is the background. We are now in NISQ era, as many of you know. In NISQ era, quantum computers are very small, which means the number of the qubits is restricted. And also, NISQ computers have large computation errors. To perform some interesting and beneficial tasks, we needed to compensate for errors. And a good way for suppressing errors is called quantum error mitigation. And after NISQ era, we'll be in the early FDQC era, early fault-tolerant quantum computing era, where we can perform quantum error correction, but the scale of the quantum computer cannot be scaled free. And after that, the era of long-term fault-tolerant quantum computing era will come, where we can perform really out of tasks like famous Shewhar's algorithm for prime number factoring, and a very complicated Hamiltonian simulation for simulating a lot of quantum systems useful for drug discovery and material design and so on. And possibly we can also perform HHL algorithms, which is useful for machine learning tasks and so on. The development of the quantum computing will be expected like this. Okay, then I'd like to talk about what is quantum error mitigation. As I explained, current NISQ or near future hardware have the restricted number of qubits. And in addition to that, the error is quite the effect of errors is very significant. So we needed to suppress computation errors to extract useful results from quantum computers. And historically, the solution is like encoding and error correction. So it's like, we encode one logical qubit with 10 to hundreds of qubits. And using the redundancy of the qubits, we can protect the computation from errors. But when we adapt this strategy, the number of the logical qubits is significantly reduced, but the number of the errors in NISQ era is strictly restricted. Like, this SCAMO device from Google has only 53 qubits, and the largest number of the qubits is like 127 from IBM. So we needed to have the alternative error minimization technique, and that is quantum error mitigation. Okay, the algorithm of the quantum error mitigation can be summarized as follows. Like, we parallelly perform the quantum computation, and we measure the result. In quantum computers, and we send the measure the results to classical computers, and the classical computer post-process measure the results sent from quantum computers, and it constructs the error mitigated outcome. And many of the quantum error mitigation protocol follows this procedure. And if you are interested in quantum error mitigation, detailed explanation can be found in my review paper in JPSJ. Okay, and I'd like to explain what error mitigation can perform. The horizontal axis is the calculation result, and many of the NISQ algorithm depends on the calculation of the expectation values of the observable. So you may assume the calculation result is the expectation value of the observables. And the vertical axis is the probability to get the result. And the blue curve indicates the noise-free circuit. And the But in the presence of the noise, the probability distribution is shifted from the ideal one. And the reason the result has a distribution is like, quantum mechanics is a probabilistic theory, and that means the result is probabilistic, not deterministic. So it has a distribution. And what we can do with quantum error mitigation is like shifting the noisy target to close to the making the noisy probability distribution around the correct results. But it has some cost. It is a larger variance of the probability distribution. That means we need to sample more result to realize the same accuracy before applying we need more samples compared with noisy-free one. And a very clear example of error mitigation is extrapolation technique. It's like the horizontal axis is the horizontal axis of the below diagram. The horizontal axis is error rate, and the vertical axis is results. And in the presence of noise, the result is shifted from the ideal value, and we cannot reduce the error from some point, from some achievable point, but we can boost the error. And by extrapolating these original points and boosted measurement outcome, we can obtain the error mitigated value. And when we set the boosting factor to 2, the formula for linear extrapolation can be written as this one. And when we calculate the variance of the error mitigated value, we can see that by using the simple formula from statistics, we can see that the variance is boosted. So we can clearly see that variance is the cost of the variance, and the samples, more samples we need for error mitigation is a cost for error mitigation. Okay, and originally, quantum error mitigation was invented for NISQ devices, but we also revealed that it's really useful for fault-tolerant quantum computing. And this result was accepted in Physical Review X quite recently. Okay, and I'd like to explain what is error correction in fault-tolerant quantum computing. Error correction is like, by encoding a logical qubit with many physical qubits, we can protect the quantum computing with error correction. And the increase of the redundancy of qubits allows for the improvement of computation accuracy. The graph shows the example of the surface code, and the value d, which is called code distance, indicates the redundancy of the qubits. And by increasing the redundancy of the qubit code distance, we can improve the computation accuracy. And the fault-tolerant quantum computing refers to the quantum computation, which perform computation while apply error correction. And the development of quantum computing will become as follows. Like we are in NISQ era, as I said, and quantum error mitigation helps disk computing to be useful for like quantum machine learning and so on. And we expect that quantum error mitigation is also very useful for early FTQs where code distance cannot be increased freely. For example, if code distance 3 is possible, it is quite unclear whether code distance 5 can be realized because scaling up quantum computer is a very difficult task. So we can utilize quantum error mitigation for improving the computation in early FTQC era, and we use technique we use quantum error mitigation called probabilistic error cancellation. Probabilistic error cancellation was proposed for NISQ device originally, but we also found that it is very useful for fault-tolerant quantum computers. Probabilistic error cancellation performs error mitigation as follows. First, we know the noise model by an experiment in advance, which is called process tomography, and gate set tomography, and so on. And after we characterize the noise model, we construct the error mitigation operation by additional operation and post-processing of the measurement result. And by characterizing the noise model on the logical space, when we use quantum error correction, we can also apply the probabilistic error cancellation on the logical space. And we found that we can realize the great reduction of the hardware resources. Like we mainly benchmark the performance in two regimes, like classically interactable regime for performing some classically interactable task on quantum computer. We expect that someday we can realize quantum supremacy also on the logical space when we use quantum error correction. And in that era, the number of gate operation should be like 10 to 4. And in such a quantum supremacy regime in logical space, the number of qubits is reduced by 80% by using the quantum error mitigation. It's really a significant reduction of the qubit overhead. And we also found that when we apply quantum error mitigation in long-term fault-tolerant quantum computing era, the qubit count can be reduced by 45%. So this technique is still useful also in long-term FTQC era. And next, I'd like to talk about error mitigation to completely different task, quantum methodology, which is also called quantum sensing. Okay, this is a timeline of the quantum computation. I showed this figure many times, and quantum information technology fields include other important applications like quantum communication and so on. And one of the important tasks is quantum methodology, which is also called quantum sensing. And the quantum methodology sensing is such a task, like estimate small external fields by quantum states with better precision. And the external fields are like magnetic field, temperature, and so on. And we denote the estimated parameter as omega, magnetic field, temperature, and so on. The sequence of the quantum methodology is as follows. We prepare the quantum state, and we make the quantum state interact with the field. And the field has the information of the parameter omega. It is like, as I said, magnetic field and temperature and so on. And we measure the results. And we repeat this procedure many times. And we obtain the expectation value of the measurement outcome. And this is denoted like Mn. N is a number of the measurements. And finally, we estimate the parameter omega from the information of the average of the measurement results Mn. This is a basic procedure of the quantum sensing. Okay, and what quantum methodology sensing can realize is as follows. In this diagram, in the horizontal axis is the number of qubits or bits, because we'd like to compare the performance with classical bits as well, classical bits, yeah. And the vertical axis is estimation accuracy. And in this diagram, the lower the better. And in quantum methodology, when we use the quantum states, we can observe the quantum enhanced scaling of the estimation accuracy, depending on the number of qubits L. And we can observe the quantum enhanced scaling than classical one. But how to say, quantum sensing seems really a promising technology for enhancing the sensing, and seems very useful. But if in the presence of the unknown noise, we perform the kind of incorrect estimate of the parameter, and this leads to the systematic errors, as which is similar to the error I explained in the beginning. Like, so the horizontal axis is the estimated parameter omega, and the vertical axis is the probability, and the blue dotted line. The blue dotted line indicates a correct estimation of omega, but in the presence of the unknown noise, the probability distribution is shifted from the ideal one. So this gives the incorrect estimate of the parameter omega. And in this case, due to this systematic errors, the benefit of the quantum sensing methodology is totally deteriorated. We need to overcome this problem, and quantum error mitigation can overcome this problem. Like, we prepare copies of the quantum state, and we apply quantum error mitigation circuit, and we measure the results, and we construct the error mitigates the estimator, and in this case, the probability distribution, wrong probability distribution is shifted to the scorect error mitigated probability distribution, and by using error mitigation, we can recover the quantum scaling. And yes. Okay, and we use that error mitigation technique called virtual distillation. This technique is like, by using the copies of the quantum state and applying the entangling gate to the copies of the quantum state, we can project the state to the symmetric subspace, and we can mitigate errors. And the example is like, when the ideal state comes with 0.9, and the noisy quantum state comes with probability 0.1. When we use two copies of quantum state, the effective probability to get the correct quantum state is improved to 0.99, and the remarkable benefit of the virtual distillation is like it works for unknown noise, so it really works for the quantum methodology tasks. And we found that we verified that virtual distillation can improve the scaling of the quantum methodology. The horizontal axis is the number of the qubit L, and the vertical axis is accuracy. And again, the lower the better. And in the presence of the systematic errors due to some non-Markov T1 noise, the scaling of the accuracy becomes the classical one. Which is totally useless. But when we use quantum error mitigation, we can suppress the systematic errors and recover the quantum scaling, which is better than classical scaling. So we also verify that quantum error mitigation is a really powerful tool, even for quantum methodology. And this is a conclusion. Quantum error mitigation suppresses the computation errors with post-processing of measurement outcomes. And we consider new application of the QEM for the first time in the world. The first one is application to fault-tolerant quantum computing, and the other one is application to quantum methodology, sensing. That's it. Thank you very much.